Thanks to TP for doing that. Um, Before I start the talk, I have something that was brought to my attention, which is I have a very funny setup with my charger. It's three different layers of adapters, and I want to play a game with you, like so, but worse, while I actually remember to mirror my screen. So, based on this, where do you think I'm from? What's your guess? Okay, UK. Go. Who agrees with that? UK? Raise of hand. Yeah? Only you. That's a bit sad. Any other guess? No. That's the like you're ruining the game. No. So, first layer, European. Second layer, UK, so not from the UK. Third layer, Italian, so sorry for that. I think it's easier to guess from the accent than from the charger. But it didn't work, so tough luck. So if you could mirror my screen, that'd be great. Yeah, let's get this started. So this talk is called Short History of Build System. And it does exactly what it says, though I'm going to indulge on a very specific build system towards the end and have a really short demo. Now, full disclaimer, this talk was 40 minutes long last time I tried it. Now I have 20 minutes. And last time I didn't have a demo in it. So it's going to be fun. It's going to be quite the journey. So we're going to go with what is a build system, how to define it, what are the properties that we care about, and how do existing build systems implement them, and how do they differ between each other, so that you can actually make a choice when it comes to picking a build system that works for you. And maybe a demo at the end. But who am I? My name is Antonio Di Stefano. I work at EngFlow. Actually live in London, so that guess was not too off. And I'm a DevEx engineer. Now, DevEx is a bit of an interesting new term for developers that worry about the developer experience in the company, so development tool chains, build processes, a sprinkle of CI/CD, and so on. You may think that that was covered by DevOps, but we like to create new terms for things that were already covered by an existing one, so why not? And I work at EngFlow, which is a company providing what we call remote execution for builds. So we basically allow you to run your build in the cloud, but not only that, scale it up horizontally to stupid numbers. Like instead of running with a parallelism of 16 cores, you can run your build with a parallelism of 1,000 or more, because we employ this technology developed inside Google that allows you to horizontally scale up build. And I'm going to go into that a bit later. But for now, just remember this very short abstract of what that is. But the core question here is, and I'm going to build a lot on this, is what is a build system? So build system is really not that different from any other task runner. The main difference you can think of is that instead of declaring an explicit order, the order is computed from your dependency graph, from what you want to generate and from what you want to generate it from. And they come in all shapes and forms. You're familiar with a few of them. With Make, for example, with CMake, with Ninja. You may have used Java, and in which case I'm really sorry for you. With Maven or Gradle or whatever else they have. And it does a few things. It takes your code and compiles it. It runs a bunch of tests. It generates code potentially, and maybe it packages things. So it's a set of transformations that go from having code that basically does nothing to having something that you can execute somewhere, or trying it out on your own system. And this is not too complex of a definition, but what is that we really care about? So as developers, we like to write a lot of things, try them out, and keep writing. Like, we want to be productive. We want to continue building what we have to build. Like, our job is not waiting for a compiler to compile. It's not waiting for hours for tests to run. is to write code and come up with interesting solutions and systems. So two of the most interesting properties that are often connected to each other are speed and efficiency. Why do I connect them? Because if by efficiency we mean doing as little as possible, that also implies that you can go faster by doing less every single time. And that's a really important property to guarantee for a build system. We also have reproducibility because it's not fun to run a build twice and end up with something that doesn't work, though your code has never changed. That's definitely not something fun to debug. We want to be able to configure the build system because every one of us has different needs for the product that they're developing. And you may need something special in your build, and you don't want to have to come up with incredible hacks to make that work, right? The moment you have to resort to like a few thousand lines of bash to be able to change your build, then the build system has failed you. And in a similar vein, you need to be able to extend it. And you need to be able for it to work. You need to have it work kind of well with the tools you already have. And that may vary. Like at a core, you need it to be able to work with your IDE or with your editor, at least a little bit. So discovering the source that has been generated and so on. So tools that come together with a build system or can cooperate with a build system are also a really important thing to look at. And so let's start with an history of build systems. And historically, you can think of the first build system as a do-it-yourself build system. So write a bunch of bash, and it kind of works. You get something out of it, compile 2 files, 3 files, whatever, and then run the test. It works. But you can already see that there's a few problems with that. It's not going to run on all platforms the same way. So not very portable, and you need to have a lot of setup in each workstation for it to work, right? You need to have the whole environment set up because the bash script in itself has no knowledge of it. It's really hard to parallelize. Like, unless you really want to parallelize it, then you're going to struggle a lot. Like, imagining having to hardwire the structure of your dependency graph in a bash script. That's like, if you can do it, good for you, but it's going to send you insane. Bespoke configuration, everybody can bash in a different way, and we do. So it can really hurt readability and maintainability. It's not integrated with tools. 0, like, good luck. And you cannot trivially build a subset of the build, so unless you build that knowledge of that build graph inside your script, you cannot easily say, oh, I just want to build this small target rather than the whole build. And it's even harder to say, I just want to rebuild this small thing because nothing else changed. So you have to wire that knowledge in the build system yourself. You are developing the build system. And that's not great because most of you, except me and a few other people in this room, don't work developing build systems. And even I hate to have to configure the build system to run a build. And so solutions have been created. Let's start with Make. And you can already see that it is a bit of an improvement. You can already start recycling a few things, which you could have done already before, but there is some recycling going on. There is some structure. But most importantly, there is a dependency graph. Like, no matter how naive, there is a dependency graph. And now you don't need to embed the knowledge of how a build is built because it's something that can be inferred from this graph, from this structure. So you declare how you want to build things, and then you say that some have dependencies with each other, and then the build just magically happens. Now, it's already better also because you can already start caching some things. So if you look at this build, if you change main or you change test, but you don't change lib.cc, you don't have to rebuild lib.cc. So you're already not rebuilding the full build. So the system has been able to cache part of the build because it now has a knowledge of what it has to rebuild when you do certain changes. So that's a good start. You can also parallelize things, which makes them faster. And it can be used with any language and platform, but it's hard to reuse things, which is going to be more important later. It's also just as portable as the shell script we just wrote. So it doesn't really excel on that end. And the caching itself might be a bit naive because it's based on the timestamp. Really, even if the timestamp changes, but the file has not changed, it will not yield different results, in theory. If it does, that's a problem. And it's kind of hard to read. Like, we've all stumbled upon makefiles that are longer than the code base itself. And that's really interesting when it happens. And unless it's something that has been generated, like via CMake, then it's basically unmaintainable. And that's the state of a lot of very well-known code bases that are now considered legacy, maybe. But let's now look at CMake, because it's a big step ahead. And I think it introduces a few very interesting concepts. Like, now we can build very reusable builds, because we have very abstract targets like add library, add executable, which explain what they're doing instead of having you write specific commands each and every single time. Now we've built this abstraction where you have inputs, you have outputs, and you have a very abstract action rather than the command line itself. And then it's all generated from there. And you don't have to worry about it. You don't have to worry about how the build works, not too much. You can also define custom targets, so when you need it, you can still run a very specific command. And so that's great because it adds reusability, and you still have the same properties with caching and so on, because the underlying build system has not changed since. So it could be Make, it could be Ninja, but you have an underlying build system that guarantees these properties. But it is way more portable, because now the same build file can be used to generate build files for other build systems in different platforms that can also behave differently. And you can build very custom logic that is somewhat still readable for different platforms. And to be honest, CMake has some pretty nice support for tooling, which is something that other build systems lack. And that I quite enjoyed. But most importantly, my favorite feature of CMake is that someone built a retracer with it. And that's pretty cool, honestly. But you still have the same problems that you have with the underlying build system. So it's still not completely portable. The caching is still a bit naive, and that's it. And then you have this very infamous family of build systems, which I'm not too keen on, which is language-specific build systems. So things like Maven, sadly, Cargo, whatever. I hope there's not too many Rust people in here. I'm risking my life. And those build systems are nice to use, but they're not exactly the best thing to use. Like, they're going to work out of the box. So you usually just have this single file that defines how a build works, and it automatically works. You don't have to configure anything. It's just going to work out of the box. And all the tooling is going to work greatly with it, because that's the standard for a given language. Now, the problem with it is that when you have more than one language in your code base, you're kind of screwed. Now you need another build system to coordinate and build systems for every single language you have, and that other build system may just be shell. So like, we're back to the initial starting point where we have glue code that makes sense to nobody, and it's unmaintainable. And it will rebuild everything, because why not? And if that's not enough, it's really hard to tune these build systems, right? They are not necessarily engineered for performances. They're engineered for simplicity, and they do that rather well. But they don't necessarily have the most granular understanding of the build graph. So you change something, you're very likely to rebuild everything. And you can't do any tuning, whereas with CMake, with makefiles, and so on, you can do a lot of tuning because you have access to the very granular targets, and you can change how they are defined. And so now let's start talking about that famous build system that I was initially introducing. This is Bazel. Bazel is a build system developed in Google. It's been developed for a really long time, no idea how long. And it was an internal product called Blaze. And Blaze still exists. But now, and Bazel and Blaze share a common core, which is most of the code base itself. But they're still a bit different. It's quite an interesting build system. In it, it supports pretty much any language you can think of while still being reasonable. So every time I mention that, somebody in the audience asks, does it support PHP? And does it support COBOL? And I find that really depressing, if I'm honest with you. And so please don't ask me that question. And it's At its core, it's designed for a code base of the size of Google, and Google is famous for using monorepos. So we're not talking about thousands of files, we're talking about millions of files and billions of lines of code. You can only imagine how slow that would be unless you engineer builds for scale. And that is done in a few very interesting ways. One of the ways that Google achieves this is through what I mentioned, remote execution, which is what my company works with. And so instead of running your build on a single machine, you run each individual action on whatever instance you get in the cloud. And in order to do that, Bazel has you statically declare all the inputs and all the outputs up front so that it knows what you need to run an action in a remote environment that is completely sandboxed and clean, and what's going to get out of it. And that makes build extremely, extremely fast. Like once you can guarantee these properties, you can get build to run remotely to a level of parallelism that is unmatched by other build systems. It does require you to work a lot on your build files, so you need to be able to capture all those dependencies really well. But it also leads to you to be able to do a lot of tuning. But I'm talking about it as if it's the most complex thing to work with. But the reality is that for most people, Bazel doesn't look too different from what CMake does. You have a lot of abstraction. You can create macros and functions and rules, are kind of like functions for CMake. And for any language you can think of, they've probably already been built with the most sanest default you can think of sometimes. Not always. And it's not hard to comprehend. It's based on a language that is kind of reminiscent of Python, but numbed down. So it's using a stripped down version of Python as its configuration language. And you can build all kinds of things with it. You can run Docker. You can build Docker images. You can build a Scala code base, a C++ code base, Java code base, and you can merge things up together because you have support for all these languages. And so it's easy to extend it. It's already most likely been extended for your needs. And so in that sense, it's quite a useful thing because whatever technologies your code base is already using, it can morph to supply these demands. It also supports remote caching or remote execution out of the box. Sometimes you do need to do some work in case, for example, you're using a binary that is present in your system, but it's not present in the remote environment. So sometimes you do need to do a little bit of work to make this work. And because it makes you declare all the inputs and outputs up front, it's very good at caching things, because if the inputs have not changed and the command has not changed and you're still expecting the same outputs, then why should I rebuild it? And that leads to to basically Bazel's motto, which is fast, correct, choose to, something like that, which is, I mean, it is true, but really it should just be about correctness, because once you have correctness, then you can guarantee that you don't have to rebuild a lot of things when you change the code. You have to always rebuild the minimum set of changes. And so it should just be correct. You get fast for free, as far as I'm concerned. And I think this is often overlooked, but it's used by giants in the industry, like Google, of course, because they developed it, Uber, Dropbox, SpaceX, and so on and so forth. Like, the list is really long. And so the knowledge that is now present on the market about this build system, there's a lot of it, and it's really advanced knowledge. Like, you can just start Googling stuff about Bazel, and you get the craziest blog post about performance improvements that you can think of. And sometimes it's kind of mind-boggling what you can do with it when you can bend the build system to your needs. Sadly, though, very sadly, though, the tooling is not great. Especially the IDE support is kind of not there yet. It can improve. That's, I think, the worst pain point that I have. And it can be quite intimidating, because when you have that feature set, the API surface of the build system is huge. Like, every now and then I discover something new, and I'm kind of shocked by the things that now I can do with that new knowledge. But it also makes it intimidating. It also does not allow you to define dynamic dependencies, which may or may not be a problem. Ninja, for example, does. Buck2, which is a build system developed by Facebook, which is very similar to Bazel, does allow you to have dynamic dependencies. But at the end of the day, that's not the biggest problem ever, because there's a family of tools called Gazelle for Bazel that allow you to generate build files. So often that's not the biggest problem ever. So let's get a bit more into detail. Let me introduce some concepts that Bazel has so that you might be able to try it. First of all, the basic concept you want to look at is the target. And the target is basically something that generates something else. It has a variable number of input files, variable number of output files, and a variable number of actions. And now you're like, what is an action? Well, an action is something that generates something else. It's basically running that command. There is a subtle distinction between targets and actions in Bazel, whereas a target has multiple actions. So it is generating things, but it's doing that through a potential chain of actions. The next concept is workspaces. And it's basically just a Bazel project. And a workspace is marked by the existence of the workspace file. And so if you have a subdirectory with a workspace file, that's not going to be considered part of the original workspace. But any other subdirectory without it will be. So it's basically a marker to say, hey, this is a Bazel build. It's like the CMake list file of Bazel. Then we have a package. These slides are a bit broken. Interesting. And a package is just a subdirectory with a build file in it. And the build file is the one that actually defines how to run things, how to run the build, whereas the workspace is mostly used to define the root of the project and define dependencies like, oh, I want to be able to build for this language, so I need to import a few dependencies for this language. And that's what you use the workspace file for. Then we have labels, which are a bit of an interesting concept in Bazel. They're basically unique identifiers for a target. And they follow this syntax of at the workspace name, then the package name, and then the target name. But this syntax can be collapsed in many interesting ways. You're usually just going to refer it to a shorter version without the workspace name if it's inside your code base itself. And if it's inside the same package, you just need to have the target name. So it has very interesting semantics, but you can usually shorten it by either package name, target name, or just the target name. Then we have build files, which we just talked about. They're a place where you can define the steps of the build and the various targets. And they can use either macros or rules, but you cannot define macros and rules inside build files themselves. Just so that like the build itself stays a bit clean. It's just a case of separating builds and the extensions of the builds and forcing developers to do so. It's more of a aesthetical choice than anything else, really. And these are rules. So let's look at a rule really carefully. So a rule is just pretty much a Python function, except it's not Python, it's Starlark. They're almost the same though, so who cares? And you define an implementation, what attributes a certain rule has, and what are the outputs. This is an abstract definition, so you can reuse it for various targets of all kinds. And it's the first reusable block in Bazel. But the API of a rule is quite complex. So they came up with a different mechanism called macros, which are exactly what they say. They're macros, pretty much the same as CMake, and they're going to expand. And in this case, I've built a macro that defines both a library and a binary from the same target. So it's going to expand to these two different targets. Sadly, though, my least favorite part about Bazel is how it's configured. It's configured through a plethora of flags because Google really likes their flags a lot. And so you have a list of hundreds of flags in the Bazel documentation, and they all do really interesting things and sometimes have the weirdest semantics ever. But for most users, it doesn't quite matter. What I find really interesting and I want to show is just like how you start using remote execution. You just specify an endpoint, and it kind of works out of the box when you do so. And I'm actually going to show that. So I'm going to build a very small C++ project. And if you have any questions, just stop me, because I surely hope that we have enough time, right? All right. Yeah, I've been rapping here at this point. So as we said, what defines a Bazel project is the root file workspace. So let's create a workspace file. We can leave it empty because we don't have any dependencies. And then we need a build. So let's write a build.bazel file. We also need some C++ because that's what we're going to try to build. So let me see, open a more decent editor for a slide. Main.cc. We're just going to do an hello world. So, are you stream right? Damn it. Nothing crazy. Like we really don't care what we're trying to run here. And now that we have some source code, let's define the build. Because I think it's kind of intuitive. So we just need a binary, right? And we're gonna call it hello, if I can type. That happens to be really, really hard. And it's gonna have some sources. Nothing new here. It's an array of strings. In this case, main.cc. And that's it, actually. We're done. We've defined a very simple build with a single target, nothing else. We can also alternatively use globbing if we don't want to write targets manually. So it is, you have to declare the dependencies and the inputs of a target statically, but that doesn't mean you have to do it manually. So in this case, you can glob, and when you run the build, when it starts the build, it's going to discover what those targets are. So now if I did everything correct, I should just be able to do Bazel build. Hello. And you see it's doing a lot of things, but really just had to build a few targets. And you can also run it. So if you have a binary, you can run it, and it prints this. Nothing crazy here, but I'm going to try to do something interesting. I'm going to try to introduce remote execution to the picture. So at EngFlow, we provide this image for free, this very small container to start. Yep.
So this doesn't generate a makefile or something like CMake, right?
Sorry, can you repeat the question?
So this doesn't generate a makefile or something like CMake, would it just generate?
No, this is an actual proper build system.
Okay.
It does the build itself. It's
good.
not scared of builds. So let's try using remote execution, because it seems a bit daunting, like, oh, your builds have always been running locally. Now they're running somewhere in the cloud. And like the single targets of the build, they're not even running on the same instance. So what is happening under the hood? So let's try running this simple Docker container. So Docker run, yeah. And it tells us how to configure this build for remote execution. So it's just these properties. Where to run actions remotely, remote executor. Where to cache artifacts, remote cache. And these last two attributes are used for this reporting protocol that you use together with remote execution. So it's this companion of remote execution that rather than worrying about the build itself, it just sends metadata on the server so that we can build a nice UI and have analytics about your build itself. So we can simply just pass these flags here, or use something called a Bazel RC, which is a way in Bazel to group flags inside a set of configurations. So now if we say Bazel config EngFlow, it's going to expand to all these flags. So let's do that. Bazel build config EngFlow, and let's pray all the gods of demos that this actually works. It's taking a long time. There we go. What? Yeah, no, we didn't pray hard enough, and now we're stuck with a build that is not working. That's sad. But But normally, this would actually work. So trust me on that. And with that, it should just build the build remotely, the same way that it builds locally, and just provide you with a URL to look at the build itself. So try to keep this very, very short. Because last time I got a bunch of questions. Before I go to the questions, though, there are lots of useful tools that you can use to improve your experience with Bazel. One of them is Gazelle, which allows you to generate build files, so you don't really have to worry about that. Works really well with Go, which is what it was created for. But it can be extended to other languages. There's a generator for JavaScript, for Java. There's a few others. I'm not sure there is one for C and C++, so tough luck. Then you have something called Buildozer, which allows you to edit build files in bulk. So you define transformations of your build code, and it does that automatically. We have a version manager, we have migration tools, and a list of all these tools, because now there's too many of them to fit in a single slide. So I'm not going to. And if you want to reach out, you can reach out on LinkedIn or via email. And yeah, if you think that Bazel is interesting, please have a look. That's it. Questions?
Yep. What about includes? Like in your Bazel file, you said, well, this target gets built from that source file, but I'm one of these crazy people of including headers and using headers that include headers, and those again might include headers.
Yeah.
And if I want to send my build to your Docker container, then probably I should send all of these headers along. Like so.
Yeah.
How does Bazel know what it needs to send there?
So it's an interesting question. So in that case, you've basically had to define other libraries, and those libraries have transitively defined their dependencies, which are going to be carried along, or the headers that they have. So that's how Bazel looks at these things. It has a mechanism for each rule to propagate additional information. So whenever you write a rule, you can return a set of informations. You can return the default info, which is I've generated these outputs. If you want to run this target as a command line, you have to also have these files in the path. But there's also custom things that you can return. So in that case, you can say, and that's probably how Bazel implemented it, this library also brings along these headers, but also these dependencies. And so Bazel automatically gathers these things when executing the rule and carries them along to remote execution.
I think you can actually add headers here, right? The section for the
binary.
binary.
So there's actually an attribute called headers.
Yeah, and also you can define library like header-only library as a target, and then like use it as a dependency, and then Bazel will know what it will need to send.
Yep, exactly.
So it's not like CMake, which tries to open the source file, look for the include statement, and then build its own preprocessor.
Was that a question? Because I didn't hear it. All right. Microphone.
Yes, I have two questions. First, so if we're not talking about parallelizing this to 1,000 cores, how does this compare speed-wise to something like Ninja? Is it fast or?
It still is fast, and there's a few reasons. Well, now we get into the nerdy bits. Thanks for the question. So I did not include these few things about speed because that's another talk that I've done, and that's like 1 hour and more than 1 hour. But there's a few things that Bazel does to be as fast as possible. The first thing you can think of is that if you're working with such huge code bases, you don't want to relook at all the build files every single time. So Bazel either watches them or it tries to keep as much of that state in memory. So the first optimization you have is that Bazel under the hood runs as a daemon. And so it can observe the state of the builds as it changes, so you don't have to recompute the whole build graph, which already makes it rather fast. Or it just keeps some state in memory, which is already a good way to speed up your builds. Another thing that Bazel supports is something called persistent worker protocol. So it allows the author of these rules and to define a daemon-like command, and that can stay warm throughout builds and keep some state. And by keeping that state, it's much, much faster than rerunning the whole command again and again. It's less visible in languages like C and C++, but think about a language like Scala, where the compiler is written in Java, and every single time you call the compiler, you have to wait like a second for Java to start up. That's miserable when you do it 1,000 times. And so in that case, by having this protocol, you allow the author of the rules for that language to improve the performances that when comparing it to other build systems which have no awareness of daemon-like processes. So other things that Bazel does, by using a content-based tracking strategy for the cache, and by having a really stable cache that tracks all the inputs, it's very unlikely to rebuild things unless they have really changed. So unless something changes, it's not going to rebuild it, right? And that combined with the fact that the cache has all these attributes, and it can almost guarantee you stable results and predictable results, allows you to avoid running a clean command. So because you don't have to clean, there are less cases where you have to rebuild the whole word. Yeah. Right? But also because it supports remote caching, oftentimes you get cache hits from CI. You get cache hits from other developers. And so sometimes you get to benefit from the state of your whole company, just sharing a single cache. And it's also more resource efficient because you're not going to have to spin up a much bigger instance for it to only use all the cores for like 5 seconds. Because you share resources with the rest of your colleagues, maybe while you're using that 5 seconds burst, someone else is not using them. And maybe when you're not using the resources, someone else is. At the same time, because it's a shared resource, we can scale it up and down more dynamically and optimize resource usages, which you can't do once you get a CI instance. Like, you can't make your CI instance smaller.
Okay, it's cool. And then, what was I going to ask? Yeah, you touched on this with Maven. I think like most build systems are either declarative. You write some XML or TOML file or whatever, or like this like scripting language. And I think some people don't like the scripting approach because it's too free-flowing, right? What is your opinion on this? Is this the way to go, or should it be a mixture? Or
so one thing that Bazel tries to do, which let's first clarify. I really like the scripting approach. I don't necessarily like the declarative approach, and that's something I like about CMake as well, because the reality is that as soon as you try to build anything more complex, the declarative approach just becomes the greatest gunk in humanity's history. It's just impossible to read, and thus you've defeated the whole purpose of a declarative approach. And so I don't like it, and Bazel tries to do something that is in between by not allowing you to define a custom target in here, a custom, what in CMake you would call a custom function. You cannot pollute this build file with logic. Instead, it forces you to basically create a file.bazel, where you can create macros and do something, in this case, absolutely nothing, or rules. And then you explicitly have to import them from the build file. So it kind of mimics this style of being declarative while not being declarative. It allows you the same flexibility as a scripting language, but at the same time, the build files are very clean because you're literally not allowed to put any scripting logic in there. So it's kind of an hybrid approach.
So I have a sneaky third question. Why doesn't it just use Python if this is already so similar? I don't know about that. That question torments me every single night. Sometimes I don't sleep because I think about that. Matter of fact, I thought about it so hard because the theory behind this choice is that they didn't want people to have a Turing-complete language because it's too much complexity. What do you need it for? It's just a build. That probably is Turing-complete anyway, so not.
That's the thing. I didn't necessarily agree with the idea of it not being Turing-complete, so I decided to spend too much time developing Snake on Bazel. Remember that guy talking about implementing ray tracing on CMake? I'm a big fan because I tend to do the same thing when I have a chance to. So we can do Bazel build at Snake and give it a try. And so it may not be Turing complete, but it turns out that Oh, by the way, this needs some cleanup. It turns out that even if you're not Turing complete and you don't allow unbounded loops, which is kind of like the whole point about it not being Turing complete, that's how they say they prove it. If you nest things enough and run them until the heat death of the universe, then Turing completeness really doesn't matter. And so, yeah, I have beef with this design decision of not making it Turing complete and just not using Python.
Because there is a build, what was called Scone, says, I don't know how you pronounce that, for C++, and I remember that being very slow, which is why I asked the first question.
Well, in this case, this Python-like language is only used as the API surface to extend builds, but under the hood, it's a mix of Java and C++. Java for the long-running server that actually runs the build, and a fast C++ command line so that you get instant feedback when you run Bazel build, and you don't have to wait a second before it does anything at all. Questions? Thank you.